Awesome. All right. Hello, everybody. First of all, as the last speaker, I want to thank Jacob for organizing this workshop. Thank you for putting in so much effort into this workshop and this workshop series. I've learned a lot. It's an honor to speak alongside Orly and Katie. And to you all, thank you for coming. It's great to see so many of you on Zoom. I know people are on different time zones. I know John is very early in the morning, other people too. So thank you for staying awake. But you don't have to stay awake for the whole talk if you don't like to. So my talk is on nomic vagueness, the past hypothesis, and time's arrow in the quantum universe. My assumptions and starting points are a bit different from those of Katie's and Orly's, but maybe there's going to be some convergence in the end. All right, so I'm going to scroll through the slides. First, oops, let's see if this is connecting. Is it moving on screen? No, okay.
I'm not seeing any moving.
Sorry. Let me do a quick reshare. Now it's moving, right?
Yeah, we can see the moving now.
Okay. First, think of your favorite laws of physics. Einstein field equations, Schrodinger equation, what have you. Perhaps those laws are virtuous as follows. They're simple, informative, explanatory, elegant, unifying, empirically adequate. Now, are they also exact? Whatever that means. Depends probably on the kind of law you have in mind. Is it derived law? Then probably not. Derived laws can be vague, approximate, But if they are supposed to be a candidate fundamental law of physics, usually they are exact. What would it take for a fundamental law of physics to fail to be exact? When this happens, we call this nomic vagueness. Vague means failure to be exact, and nomic means laws of nature. So what is nomic vagueness? And does nomic vagueness exist in a world like ours? What does that mean for the mathematical foundations of physics and the nature of laws and the connection to other kinds of vagueness such as ontic vagueness, epistemic vagueness, and semantic vagueness? And the context of our investigation concerns primarily arrows of time and the foundations of statistical mechanics. But time permitting, we might talk about other domains too. Concerning the arrows of time, we ask the following questions. Why is the future so different from the past? Why is entropy lower in the past and higher in the future? Why do we have memories and records of the past, but not of the future? Why can we influence the future and not the past? And how can any of this be true when the fundamental equations of motion essentially lack an arrow of time? This may seem like metaphysical questions going beyond the scope of physics. However, following Boltzmann, Feynman, Reichenbach, and Penrose would suggest that these questions require a scientific explanation, something like fundamental law of nature. In the literature, there is a proposed explanation. So I'm going back to Boltzmann and develop further, and it's been discussed much in the literature recently. This is called a past hypothesis, or PH. Roughly says the universe initially, in quote, was in the low entropy macro state. Initially, in quote, because it might just be a boundary of space-time without distinguishing initial from final. So we can infer that that was the initial past state. Now, there are good reasons, I suggest, to think that the past hypothesis is additional fundamental law of nature. I won't rehearse all those reasons for now, and there are many defenses of this idea in literature, although it's controversial. But like everything in philosophy is controversial, right? The past hypothesis is part of the scientific explanation for nomic regularities, such as the second law of thermodynamics, as Katie discussed earlier. And moreover, the past hypothesis is not derived from other laws. So it has an axiomatic status. And further, pH plus plays a crucial role in our reasoning about counterfactuals, records, and influence. We might disagree on how exactly it plays its roles, but it seems to have some roles to play here. In this talk, we suggest that the past hypothesis is vague. We don't assume typicality here in the argument, although you will simplify the argument significantly, but it's controversial what typicality means, as Orly has mentioned. So it's good that we don't have to rely on typicality to make the argument. This illustrates the possibility that there can be vague fundamental laws, a phenomenon I call nomic vagueness. When I call nomic vagueness, I mean primarily fundamental laws are vague. Some of them are vague anyhow. And this illustrates the possibility because there can be other possibilities that are vague. But pH, I think, is a very clear and very nice and very simple and very accessible kind of case study. The vagueness of the pH in this case is hard to get rid of without committing ourselves to untraceable arbitrariness in nature. Discuss this more soon. So in this case, we have a dilemma between nomic vagueness and untraceable arbitrariness. However, the situation is completely transformed in a new framework for thinking about quantum mechanics in a time asymmetric universe. For lack of a better name, I call this the one-calculus package. All right. I'll explain what this means in a second. Okay, so the received view, I think the implicit view anyhow, is that fundamental laws are exact. Think of Newtonian mechanics for projectile. There is a trajectory for how it goes and how it falls. Moreover, given Newtonian mechanics, and say the force law being gravitation, universal gravitation, Newtonian mechanics, you have an exact set of trajectories compatible with the equations, the differential equations. So there is an exact indeterminate collection of trajectories compatible with Newtonian laws of motion. Think of them as collection of point particles. Now, in a space of possible worlds in the philosophy language, there is an exact and determinate set of worlds compatible with Newtonian mechanics. When we say set already, we can ignore exact and determinate, but I just want to emphasize again, it is a determinate exact set. It's not a fuzzy set or anything like that. So in the language of phase space, there's going to be a collection of trajectories compatible with differential equations of motion. Still works. A law L is exact if, for any world W, there's a determinate fact about whether W is compatible with the law L. Here we assume that worlds themselves are exact. There's no untick vagueness in the material ontology. You can make that assumption, things become more complicated. If you simplify that, then things become a bit more straightforward. Although you can define this in different ways, suppose you allow untick vagueness. Anyhow, set aside because we don't need that to make the argument. So in the space of all possible worlds, W, we have all the possible worlds, every point being a complete microscopic possible world in terms of all the details, position, momentum of all the particles, okay? Or wave function configuration, blah, blah, blah. So every circle can kind of prescribe some subclass, right? Newtonian mechanics prescribes a particular proper subclass of W that is all and only in the possible worlds compatible with Newtonian mechanics. So here W1 is determined inside the boundary, W2 is determined outside the boundary. The boundary points are determined inside as well. Similarly for L1 and L2, which are two different kinds of exact laws. So far, so good. And this ideal for exactness, I think, is implicit or explicit in previous works in foundations of mathematics and philosophy of language, and metaphysics such as Frege's Burgerschrift, Russell's logical atomism, and Leibniz' universal characters. And it's also natural to think there is connection between exactness and mathematics. Mathematics is supposed to be the ideal language for physics, right? Fundamental physics. It is exemplar for exactness. It is free from vagueness, indecision, fuzziness. And moreover, the set theory foundation for mathematics has membership relation as a fundamental relation in set theory. That is exact. Either something is within a set or something is outside a set. There's no borderline cases. So math will be a perfect language for fundamental physics if all the fundamental laws turn out to be exact. But what if some laws, fundamental laws, turn out to be vague? A tempting thought is to add some degree theoretic notion, fuzzy logics, degree truth, set measured probabilities, for example, but it's not going to work. And this has been, I think, articulated in previous works. And I am pretty sympathetic in the work of Mark Sansbury and Timothy Williamson, Susanna Reynard. We're going to talk more about this soon. So, okay, what is it for fundamental law to be vague? Here is a visual imagery of a vague law. It's like a cloud. Just like a cloud, we have some points in the sky clearly within the clouds, some points in the sky clearly outside the clouds. For the approach boundary, there's some borderline cases. There's not so clear to classify how one is inside the cloud or not inside the cloud. So the cloud has some fuzzy boundary in the space of sky points, right? Space of point in the sky. Similarly, imagine the law L that fails to have a determinate boundary in the space of possible worlds. L does not delineate an exact set of worlds that are compatible with L. It may have a fuzzy, cloudy, or vague boundary. I say that L is a vague law, at least in this sense of vague. There are other senses of vague, which we'll set aside for simplicity. I'll talk more about them in the paper. L is a vague law if there exists some world W, such that there fails to be a determinate fact about whether W is compatible with L. So if L is vague, then some worlds are close to the fuzzy boundary of L. So here is the imagery in the space of possible worlds. L1, L2 are exact, but the vague law here is vague, right, inexact. W3 is determined inside the vague law, but W4 is determined outside the vague law. But W1, W2 are close to the boundary of the fuzzy boundary of the vague law. The past hypothesis is very much like this. A vague law with a cloudy boundary. There may not be any vague fundamental law of nature. After all, Newtonian mechanics is exact. Schrodinger equation is exact. Einstein field equations are exact. The solutions form a space, a set. There are some possible cases in the history of science, such as quantum measurement axioms. It depends on what counts as a measurement, what counts as a macroscopic system, what counts as a measurer. You might have a shifty split. You might have a vague boundary between when collapses happen. I think we know better now that these theories are bad for other reasons, not just for vagueness, but also just for complexity and unpredictability. And there are also effective field theories. If they are counted towards candidate fundamental theories of physics, they might introduce some fuzzy parameters or fuzzy scales. See a recent paper by Michael Miller. I think Miller is more interested in the set theoretic kind of imprecision when you have, say, 0.4 to 0.6. It's not an exact number, it's a range of numbers. But whereas I am interested more in the fuzziness, where even the boundary is not precise, it's not exact. So I want to go further to see real genuine vagueness. A case for nomic vagueness, genuine vagueness that deserves serious consideration, can be less controversial and sometimes accepted already by philosophers of physics and physicists, is the past hypothesis, some version of the past hypothesis. We'll focus on pH for now. As a bonus, we'll talk about what the differences there are between vagueness in pH and vagueness in quantum mechanical collapse axioms. There is, I think, a principal difference lying in traceability. Some question might have. We say pH is vague. Why is it vague? Assuming pH is fundamental law, then we have nomic vagueness. Is it a feature or a bug? Why is pH a fundamental law? Why can't we replace pH with an exact version? Is there something we can do about nomic vagueness, even the bad thing you have? Okay, we'll come to these questions. First of all, ordinary kind of vagueness. It is discussed much in philosophy of language, metaphysics, logic. Vagueness permeates ordinary natural language like English, Chinese, French, and so on. They're not exact. Most predicates we use in daily contexts do not have determinate boundaries of application. Well, I think for some reason, the first person that comes to mind for non-bald person is Trump. I guess I've been watching too many news recently. So apologies. Is Trump bald if he has exactly 90,000 hairs on his head? What if Trump loses just one hair? What if he loses just 2 hairs? And ... without losing all of his hairs? This is a case of the Saraitis paradox. It seems at first, with all these hairs, 90,000 hairs, Trump is not bald. In the end, after losing all the hairs, Schramm is bald. But it seems arbitrary to pick an exact number of hairs. It turns Schramm into a bald person. After losing a certain number of hairs, before losing all of his hairs, it may be vague whether Schramm is bald. In other words, Schramm becomes borderline bald. So what is the exact interval that is the range for borderline baldness? It seems, if you think about it, borderline bald itself will be vague. And similarly for borderline bald, and borderline bald, and so on and so forth. That's the phenomenon of higher order vagueness. Well, kind of vagueness permeates up. Similarly for other vague predicates, tall, low, and red. If we follow Keith and Smith in characterizing vagueness follows, then vague predicates apparently have borderline cases, fuzzy cases in the boundary. But apparently it's added here because we want to make this compatible with epistemic vagueness. Talk more about this later. Vague predicates apparently do not have well-defined extensions in terms of sets. Vague predicates are susceptible to Serratus paradoxes. Vague predicates apparently come with high order vagueness. And it's the high order nature of vagueness defies mathematical modeling. So in analogy, I propose we characterize nomic vectors as follows. Vague laws apparently have borderline worlds and borderline models. Vague laws apparently do not have well-defined extensions in terms of possible worlds. Vague laws are susceptible to Serratus paradoxes, and vague laws apparently come with high order vagueness. So it's in parallel. Now, let me mention briefly high order kind of nomic vagueness. There should be no sharpness anywhere if a law is vague in the characterization of nomic possibilities compatible with the law. But mathematics is sharp. Mathematical theories of degrees of inclusion, degrees of truth, set-valued measures do not completely capture high order vagueness, at least not faithfully. It seems to impose more structure than there is in the objective order. They have even more sharpness than just simple-minded vagueness. So this gives us some reason to think of the following impossibility conjecture is true. It's not conclusive, but I just want to put this forward. It is impossible to adequately express or completely capture or faithfully express a vague fundamental law using the language of mathematics. It does impose something extra in the law structure of the world. Well, is it true? Is it not true? I think we have some arguments, although they're not conclusive. We'll come back to this point. Okay, so the path hypothesis. Why is the path hypothesis vague? With a first kind of glance, pH is stated in the language of macro states and macro variables. But partition phase space, partition state space into some chunks, right? The partition itself is not exact. Well, start with the weakest kind of path hypothesis, says the super weak path hypothesis. The universe initially was in a low entropy state. This might be implicit in people's version of the path hypothesis, but how low is low? This is obviously vague. I think we probably need something extra and stronger and more informative. And the harder case is the slightly stronger case that I think Albert and Lower and other people have in mind. I call this still the weak path hypothesis. It's not the strongest, so I call this the weak path hypothesis. The universe initially had a particular low entropy macro state M0 specified by the macro variables for entropy, volume, temperature, and pressure, and so on. I claim that even when the macro variables are endowed with precise real numbers, say this is some value 500, this is some value 700 in some units, pH is still vague. The issue is this: which exact set of microstates does M0 correspond to? Some worlds, some microstates are definitely compatible with M0, and some are definitely not compatible with M0, but some are borderline worlds. There are many admissible specifications of M0 in terms of different sets of microstates. They're more or less similar. Perhaps I can imagine a union of all the admissible ones, but admissibility itself is also vague. This is faithful to the high order vagueness phenomenon I talked about earlier. So instead of drawing the exact curve in the phase space, I'm going to draw a phase space as follows with fuzzy boundaries on the macro states partitions. Well, this is kind of exaggerated because fuzziness is not so prominent, and macro state equilibrium is so much bigger that you cannot even see the other macro states. But anyhow, as an illustration, I want to say that there are regions of phase space, partitioned phase space, but the partition itself is kind of in quote. It has fuzziness on the boundaries. Equilibrium is itself a fuzzy macro state. And the path hypothesis selects a special low volume M0 macro state with fuzzy boundary as well, and X0 is compatible with the vague path hypothesis. Well, if this is a precise boundary, then it's of a set, gamma 0, and X0 belongs to the set. But that's not the version here we talk about right now. That will be the strong path hypothesis. We'll come to it shortly. And moreover, for the Humeans, there's no evidence for the exact carving that strikes the best balance between simplicity and informativeness on phase space or on Hilbert space. We had hope for that, but there's no argument for the conclusion. C parameters. A different way to think about why the weak path hypothesis is vague. Both modern system mechanics invokes many arbitrary choices when try to bridge the microscopic to the macroscopic. Many choices such as coarse graining, from physical space to mu space to phase space. And we have to choose some correspondence between thermodynamic quantities, the temperature, and so on, with functions on mu space. But to choose some cutoff in the case of quantum mechanics of being in some macro state, when the wave function is spread out in different macro states. Let's call this the C parameters for coarse graining, correspondence, and cutoff. In practice, the exact choices don't really make a difference as long as we are sensible in our choices. But sensibility itself is vague. Are there really facts of the matter about what the C parameters should be known to nature? Well, I think that would be very implausible. Think about coarse graining on mu space. The equal size cells need to be microscopically large, but macroscopically small. They should be large enough to talk about distributions, should be small enough so we can connect them to some quantity like temperature. But how small is small enough and how large is large enough? There's no evidence for the existence of an exact size that strikes the best balance between simplicity and informativeness. And similarly for other C parameters, it is a vague matter. And you can do a Sorites paradox on the C parameters too. So the correspondence between macro states and sets of micro states is not exact, it's not even imprecise, it is vague. So if the weak path hypothesis is vague, and if the weak path hypothesis is fundamental law of nature, then we have nomic vagueness. Maybe nomic vagueness doesn't trouble you at all. Humeans are okay with it. Usually they're pretty, it's not troubled by vagueness so much. Non-Humeans are more troubled by it. But in any case, we can ask whether it's possible to get rid of nomic vagueness somehow. Perhaps all things being equal, we might prefer a world in which the simplest and most informative description is not vague, or a world in which the fundamental laws are exact. Of course, not all things are equal in the end. We see the dilemma between vagueness and traceability. And moreover, you want to retain maybe mathematical expressibility for pragmatic reasons. You want to think that the best system or fundamental laws can be expressed completely in every bit of them in set theoretic mathematics. So there are two strategies for getting rid of nomic vagueness I can think of, and there may be other more. First, deny that the weak path hypothesis is a fundamental law of nature. Then the question is, what kind of thing is the weak path hypothesis? What does it seem to play such an important role in our inferences about the past and future that's on a par with other fundamental laws? What does it seem to have the same necessity and simplicity and informativeness as the other fundamental laws of nature? You might say, well, it is not a law, but it's axiomatic postulate. That's okay. I don't want to quibble the notion of law linguistic data, but just still in the axiom system, in the best system, or in the axiomatic system for non-human laws, non-human theory, part of the axiom is vague. One can perhaps seek a deeper explanation, dynamical one maybe, in terms of fundamental physics, more fundamental physics. And that was suggested in the Chen model 2020-04, where they propose a mother universe giving birth to baby universes that hopefully dynamic would tell us that typical baby universes will be starting in low entropy state, sufficiently low. But there are many open questions about whether that approach will deliver plausible laws of nature, and we rule out enough, say, Boltzmann brains and the like. Anyhow, I think this is a kind of interesting open research question. The second, maybe more straightforward one you have already thought of, is to replace the weak past hypothesis with the exact version of the past hypothesis. Now, the problem is if you stay within the standard Boltzmannian framework for phase points or wave functions, an exact version of the past hypothesis will commit us to a non-neutral kind of arbitrariness that is objectionable. By the way, I want to say that this also may be a problem for a certain kind of Gibbsian approach to systemic. And in a kind of simple past hypothesis that David Wallace proposed, I think what counts as a simple law could be vague. What kind of simple wave function could be vague too. So maybe we'll carry over to those kind of programs too. Anyhow, but there's reason to be hopeful if we open to a new way of thinking about quantum mechanics in time management universe, and that's the one-tackless package. And the new approach might make one more open to accept a low entropy initial condition as fundamental law of nature. So in the end, this might actually converge back to Orley's point and even Katie's point earlier. So let's first stay within the standard Boltzmannian framework, think about this dilemma between vagueness and arbitrariness. What if there's a precise set of microstates, gamma 0, such that it is the actual precipitation of M0 privileged by nature? We call this a strong past hypothesis. The initial microstate of the universe belongs to a precise set gamma 0. So X0 is in gamma 0. In the quantum case, psi 0 is in some H0. So SPH supports an epistemic interpretation of the vagueness of the past hypothesis. The vagueness is merely epistemic due to our inexact knowledge. So here we can replace the vague partition of phase space with an exact partition. This is a more familiar one you have seen in Penrose's books and other people's works, right? And here's an exact partition, and we choose one of them, gamma 0, as the precipitation of M0 privileged by nature. This is the past hypothesis region. So X0 has been compatible with gamma 0, precise set. Everything is fine, mathematically expressible, and exact. The fuzziness is removed, and gamma 0 prime, which slightly differ from the boundary, is not allowed. It is not the actual law. However, I say that the strong past hypothesis is implausible, as it seems to me. And I'll go into more detail in the paper version, but briefly, the reason is as follows. The exact choice of gamma 0 is arbitrary in an objectable sense. It amounts to an exact size of cells for coarse graining, exact correspondence, coarse grain distributions, and exact cutoff for the macro state in quantum superposition cases. Now, you might say other things are arbitrary too. The value of arbitrary constant of nature and exact forms of F equals M A Schrodinger equation are arbitrary. There's no first principles to deduce them from. Right? Natural constants are also arbitrary. They have exact values, even though they cannot be deduced from first principles. So what's so bad about arbitrariness? Difference is natural constants have effects in the material world in the following sense. Typically, in most worlds, deemed possible by the original laws, any slight changes in the values of natural constants will be reflected in the material distribution of the matter in the world. And the world will change nomenclature status from being possible to impossible with some change in probabilistic measure. And this is the same for exact forms of other fundamental laws. We call this property traceability. But precisely, it can be defined as follows, but I won't bore you with the definition, so let's look at one example. Take Newtonian mechanics, F equals ma plus gravitational law, F equals g m1 m2 divided by r squared. So well, that's the fundamental true law. We have a space of possibilities, right? Compatible with Newtonian mechanics. If you change the constant value g from this number in the appropriate unit to a slightly different number to this one in the same unit, what's going to happen? Well, most worlds compatible with the original law will no longer possible. Similarly, if you change division from r squared to r to 2.001, most worlds will be impossible again. Similarly, for multiplication by m1 divided by this one instead of divided by m1, most worlds will no longer be possible. For typical Newtonian world, whose microscopic history H is the solution to Newtonian laws, H will not be possible given any of those changes. Other examples: the laws of dynamical constants of Maxwell and thermodynamics, Bohr mechanics, average theory, relativity theory. In stochastic theory, GRW, the original additional wrinkles about conformational measures. But anyhow, the idea is that suppose you have some law L and exact law L. Typically, any changes to some parameter O will completely change the solution space from here to this, maybe with minimal overlap. Not so for the strong path hypothesis. Unlike natural constants, the gamma zero, the precise set chosen by the strong path hypothesis, is not traceable. There's no trace in the material ontology for typical changes on the boundary of admissible changes of gamma. Most admissible changes of the boundary of gamma zero will not have any effects in typical worlds compatible with gamma zero. So think of this diagram, right? Most changes to gamma zero in terms of, say, coarse gradient scales, C parameters, and the correspondence, the cutoffs, and so on. We have only small effects on the boundary of gamma zero, such that you have a slightly different, say, from gamma zero to gamma zero prime. Most worlds compatible with gamma zero will still be compatible with gamma zero prime. And there will be no correspondence change in the thermodynamic status or property distribution of most worlds. And the same is true, and even more so, in quantum system mechanics. Think of a microstate being a wave function psi, and the macrostate being a subspace energy hypersurface inside the Hilbert space universe. In the quantum version, the weak path hypothesis says initial wave function is in some low entropy macrostate M0 specified by the macro variables, blah. M0 vaguely corresponds to sets of wave functions. It vaguely corresponds to subspaces in Hilbert space. We can formulate and stipulate a strong path hypothesis in quantum language. Particular subspace H0 that has very few dimensions, has it has an exact low entropy for Boltzmann entropy. So dimension of H0 is blah, a number. And that will give you a low entropy for the initial wave function. The quantum strong path hypothesis says the initial wave function universe is completely inside H0. No vagueness, no fuzziness, is a complete set. But this also has implausible sharpness. Now even more implausible because we need to commit ourselves to another C parameter not present in classical system mechanics. The wave function can spread out in different macro states. Now you have to say what is the cutoff range, what is cutoff parameter for saying which wave function is which macro state. Okay, so we have a dilemma in the case of the path hypothesis between nomic vagueness and untraceable arbitrariness. Now, it's not clear what to keep and what to avoid. I myself want to keep traceability and be okay with vagueness, but you might have different opinions. And it might be desirable to maintain mathematical traceability of fundamental laws for pragmatic reasons, maybe, or for some other commitment to rationalism. The universe is intelligible in a way that mathematics says it is. It can be mathematicized completely. But it might not be, something followed from empiricist perspectives. Also, you might want to maintain a tight connection between the nomic and the ontic. That law should leave a trace in the world, in typical worlds. It should not be completely arbitrary in some sense. So the conservativeness and continuity with history of science are not clear cut because all the previous paradigm cases of laws are both exact and traceable. By the way, let me mention briefly that traceability is a novel theoretical virtue, but I think it is an important virtue to keep in mind. It does explain why we're more okay with a vague path hypothesis than the vague theory of quantum mechanics. So what can be the principal difference between the two cases? for the weak path hypothesis, its exact alternative strong path hypothesis with strong, precise boundaries is untraceable. But for the vague measurement axiom, its exact alternative is in fact traceable. Different cutoffs, different way to remove the shifted split between macroscopic and microscopic to remove, to say when exactly does the wave collapse, will typically lead to differences in the fundamental material distribution of ontology, how things are distributed in space-time, wave functions, or fields, or particles, or collapses, and so on. All else being equal, if we can avoid nomic vagueness without committing ourselves to untraceable arbitrariness, we should prefer an exact alternative, all else being equal. But not all else being equal in this case, in the weak path hypothesis. If we can do it only if we commit ourselves to this kind of arbitrariness, then the fundamental yet vague law is perfectly acceptable. That's why we should be okay, I think, with the weak path hypothesis being vague and being fundamental, and yet we should not be okay with a vague quantum mechanical measurement axiom. Okay, so there's a dilemma between vagueness and arbitrariness. In the standard picture, Boltzmannian and source mechanics, space point and wave functions. I think there's a way to dissolve the dilemma in this context. It's very surprising to me, and actually it lies within quantum theory. Let's try a different approach to Boltzmannian quantum system mechanics. 2 steps. First step, density matrix realism. Propose that the quantum state of the universe is objective and impure. And this has been proposed in literature by others, but not necessarily endorsed, including Dewar, Ghostin, and Zangi, and Tomioka, and Wallace, and Moroni, and others. It was actually discussed also in Bell's earlier papers in connection to de Broglie-Bohm theory. So this part is not new. What's new is next step. But anyhow, I'm thinking that suppose we take density matrix realism and think of the quantum system mechanical microscope universe being an impure density matrix W. The density matrix W will then enter into dynamical equations. It guides Bowman particles in the new guidance equation in W quantum mechanical theory. It collapses spontaneously in the new collapse equations, generalizations of the original collapse equations, and give rise to emergent multiverse in WQM. And this was proposed by DGZ and also Moroni. And this was proposed in Allori and co-authors. This was proposed, I think it was discussed already in Allori and also discussed in Wallace and others. Okay. Now, that so far is, new, but still standard. The next step, I think, is the novel ingredient here. So you can still say, well, the original density matrix can be anything you like, compatible with the path hypothesis, right? You can actually have a density matrix distribution over density matrices that are fundamental. So far, you still have vagueness there. But what is the initial microstate density matrix like? I propose that there is a natural choice given pre-selected low-dimensional subspace H0. I call this the initial projection hypothesis, or IPH. The initial density matrix W0 of the universe is a normalized projection onto some low-dimensional subspace H0. It's pre-selected. That is, W IPH at T0 equals to some projection operator to this initial subspace divided by the dimension of the subspace. This view leads to the Ventaculus package. Ventaculus is derived from the word mentaculus, where Albert and Lower took the word from a Coen brother movie, A Serious Man, and this is supposed to be the probability matter of the world. And now I'm using when W because W stands for a density matrix. It's a terrible name, but someone has a better suggestion, let me know. For more details on the connection to other topics such as quantum ontology, wave function realism, Higgs supervenience, and chance, empirical equivalence, here's some papers on arXiv. This is on density matrix realism, IPH. This is the main paper. This is on Higgs supervenience, and this is on STEMMAC probabilities. This is on empirical equivalence. Okay. So the view leads us to see the following. instead of having many possible initial wave functions or even possible initial density matrices to choose from, we have now only one possible initial quantum state, WIPHT0 equals this. That's privileged by dynamics. It got two roles to play. First, the macroscopic role. It corresponds to low entropy macro state, H0. But also it does have a microscopic role, unlike the usual density measure, measure over phase space. It describes the actual microhistory by being part of the dynamical equations of motion. It guides Brownian particles, undergoes geodynamic collapses. It gives rise to different branches of the ever-rotating multiverse. It is there in the ontology, in the nomology. So the initial density matrix in the initial substage H0 becomes traceable. Different choices on initial W0 in my theory will lead to typically different histories of the micro-ontologies in the ontologies. Okay, here's a clarification. I need to clarify here. Absolute uniqueness. Didn't we say that H0 was pre-selected, the initial subspace? Would there be lots of good choices? Would be borderline good choices of H0, maybe also a vague matter? Here, we distinguish between theory construction and theory evaluation. After we are done formulating the theory, you can look at the complete package. Given a particular microhistory, there's likely only one, or in some situations, determinate set of choices of WIPHT0 that is possible, or most likely. The sharpness of IPH is not arbitrary. It is traceable in the ontology. Put its role in the ontology dynamical laws of motion. So we can commit ourselves, we can postulate IPH without committing ourselves to this kind of objectable, untraceable sharp boundaries in nature. In analogy, WIPHT0 is more like a constant of nature. It has an exact value, we can measure it with more and more precision. It has objective anchor in the microhistories. Sharp boundary is no longer objectionable. So Nomic vagueness disappears. Laws are still traceable. Dilemma is resolved, at least in this case. In conclusion, I have proposed a general account of Nomic exactness and Nomic vagueness in terms of existence of borderline possible worlds. And we'll look at one, I think, pretty clear and simple case study, the past hypothesis. It gives rise to different interesting issues that were not expected, and you have to look closer, you have to think carefully. And the dilemma in this case is between Nomic vagueness and untraceable arbitrariness. The dilemma is dissolved in the one-calculus package because of the role the initial density matrix plays, microscopic and macroscopic, dynamical and giving you a macro state. But this is surprising. Quantum theory is supposed to be giving you fuzziness, vagueness, shiftiness in the world. But actually, we show quantum theory removes vagueness from the laws of nature. For more details, see preprint version on arXiv. However, Nomic vagueness might come up elsewhere in the final theory of physics. Hopefully, then, the lessons we learn from this case study, the past hypothesis, can transfer to those cases. We have to be careful and think about the trade-offs in these individual cases, look at a case-by-case method. But I suggest we have an empiricist attitude, be open-minded, be willing to revise our old principles. Perhaps not all laws are exact, and then that may mean that not all laws are mathematically expressible. But if you don't like this, you might want to try and reformulate the foundation mathematics for physics that refuse the following possibility conjecture. And that would be very welcome indeed, not only for physics, but also for vagueness in general. Either way, you'll learn something surprising. Vagueness not only permeates ordinary language, like English, but it can also arise in the objective nomological order. Vagueness might appear in the world, not in the objects, but in the laws of nature. Or we might need to rethink the foundations of mathematics, if mathematics to remain to be the ideal language for physics. And that's all. Thank you for your attention. The end.
Great, that was fantastic. Thank you so much, Eddy. So if people want to raise their hands, I can start calling on people. I think the first hand I saw was David Albert. Go for it.
Hi, Eddie.
Hi, David.
That was great.
Thanks.
I have a couple of questions, but let me just pick out one. When you were distinguishing between exact laws and vague laws, you didn't say much, as I recall, about probabilistic laws. Think of probabilistic dynamical laws, like in the GRW theory. Do those, I'm presuming you think those count as exact, but I just want to make sure. And if they do count as exact, how does the criterion you used in terms of a trajectory being compatible or incompatible with it apply in those cases?
Yeah, thank you, David. That's a great question. So going into more detail in the paper version, and I left it out because I think it'll be maybe complicated the issue a bit. So exactly, I think probabilistic laws raise different kinds of questions. And you might have a complete domain compatible with many different measures, different probabilistic measures that can have vagueness in which measure to include in the fundamental theory. But the world domain is exact. So I think of those. So intuitively, if GRW theory postulates precise exact parameters, probability measures or constants, per unit time, per unit particle, and so on, that's exact. And of course, we have a typicality understanding of GRW that's not exact, it's vague.
Okay, but suppose we took the first option, okay? I don't understand why we couldn't do exactly the same thing with the past hypothesis. That is, we replace the past hypothesis by some exactly specified probability distribution over initial conditions. Okay.
Right.
Then what we have both in GRW and in the past hypothesis, say in classical mechanics, is some probability distribution over possible trajectories of the world, an exact probability distribution over possible trajectories of the world. It may be very hard to empirically distinguish, both in the case of GRW and in the case of the past hypothesis, which of them is true, because the effects of small changes may be very subtle. But it feels like both of them amount to perfectly exactly defined probability distributions over world histories.
Yeah, that's very helpful. So I go into this more in the section in the paper, exactly corresponding to this word. So think of GRW for now. Suppose it is exact. Now, in what sense is it traceable? It's not in the original sense of being possible to impossible trajectory, but in the sense of the trajectory, its macro history, has some changes in the probabilistic measure it receives. So changing
same with the probabilistic past hypothesis.
Yes. No,
Okay.
sorry. Let me just clarify this a bit more. So GRW theory, you have some changes in the lambda or some changes in the per unit time parameter. Then the typical history may not confirm the original theory, the new theory anymore. So there's a uniquely most confirmed theory in GRW, but not so much in the past hypothesis, probabilistic version. Suppose you have a pH, and suppose you have many different measures over the pH macro state. In general, there will be many different measures that give rise to exactly the same probability measure on the typical trajectories.
Wait,
conditional probabilities on various points and so on will be exactly the same on different choices of measures. And also, there's no precise boundary on which set are allowed. We have admissibility criterion too, which probability distribution is admissible and which is not. So that would still be vague.
No, but wait, and I don't want to belabor this too much if I'm just missing something, but forget about talk about macro states. Just entertain as the right way to write down a past hypothesis, different probability distributions over initial microstates, okay? Forget about whether they're linked with macrostates or how they're linked with macrostates. We just have a bunch of different probability distributions, okay? This seems formally identical to a bunch of small variations in something like a GRW theory. That is, they're both probability distributions, exact probability distributions over world histories.
Well, I think it's not formally exactly alike. They're similar, but not alike. So I talk about the coin case in the paper. Think about a coin, a biased coin and a fair coin. Fair coin, 50-50. Biased coin, 0.51 versus 0.49. For any history, right, there will be, in general, typical history, there'll be uniquely confirmed, most confirmed hypothesis. Is the coin fair or biased towards this, to this degree, with 0.51, right? And in GRW2, in given 90 microhistory, there's a most confirmed version of the parameters, but not so much in past hypothesis, right?
Well, wait, when you say not so much.
So the parameters here is not a one parameter difference, right? So in the case of coin hypothesis, you have one dimensional variations. In the past hypothesis, there's so many different ways to vary the probability distribution and the set such that you can cancel out each other to give you the same condition probability on these trajectories. You have the same posterior probability for many possible measures. And moreover, the set of measures is not determinate set. The set of measures is vague too, because what counts as admissible measures is vague.
Okay, I think there may be more to say about this, but I'll leave it there.
Okay, thanks, David. Yeah.
Great. Actually, if I could just quickly follow up on a point that came to my mind from what David was saying. So one question one can ask about this story of the past hypothesis, right, is this distinction between laws and initial conditions. The reason I think of the past hypothesis as more of a law than initial condition, not only because of its implications for its importance to other laws like the second law, but also because the past hypothesis is not the statement of a specific, micro world initial condition. It's a general statement about what class, at least in the classical sense, what class, what macro state, what collection of possible microstates we're going to say are okay, that give us the low entropy that will lead to the universe as we see it evolve. When you go to the quantum case, in a sense, what you're kind of doing is taking like an exact precisification of that macro state. You have this sort of gamma naught, and you're replacing it with a density matrix. Because in a sense, if you take sort of a realist point of view to the initial density matrix of the universe, then different density matrices will have different effects. That they'll get different traceability in the resulting universe. In a sense, what you're doing is you're taking what I thought of as a law, the past hypothesis, which didn't specify a single initial condition, and replacing it in quantum mechanics with a specific initial density matrix that, as you said, we could in principle go and investigate and maybe even determine. And then it goes back to being not a law, but an initial condition. W is now a specific initial density matrix that you could plug into an appropriate, equation of motion for the universe. So in a sense, are we, in the Wentaculus approach, are we not so much finding a non-vague past hypothesis law, but replacing what was a law describing what kinds of initial conditions we could have with just a specific initial condition, in which case it's not a law anymore. The reason I say this came up from David's point was because, in a sense, stating a probabilistic law is in a way a little bit analogous to specifying like an initial density matrix, saying that rather than there's some specific microstate, that actually what we're saying is the initial condition is this collection of, is this particular probability distribution. So is that kind of what we're doing? We're replacing a law governing what kinds of initial states we could have with just a specific initial state, in the Wentaculus approach, a specific density matrix that is our initial state. And I guess in the approach that David is talking about, a particular probability distribution and taking that to be like an initial state.
Well, so thank you for the question. So I don't think, the restriction intercondition from infinity to 5 will make this not a law, but to 1, exactly 1 interconditions will make this less law-like. I think it depends on the simplicity and informativeness and roles you play in the theoretical structure. And it seems like it's not any density measure can play this role. Many density measures typically are going to be very complex to characterize. So the hope is that there's going to be a simple one and plays the dynamical role in the one-calculus theory. There's also replacing the vague past hypothesis. The removal of vagueness because the dynamical laws actually does, use the inner density measure to characterize, say, particle motion in Bohm mechanics, collapses in GRW, in average multiverse branching structures. It is not just saying it is objective or real. So density measure realism plays one part of the role, but the second part is by using this inverse projection hypothesis, using this to characterize motion. And I think, just to go back to David's words earlier, I think the main reply is that in the case of the past hypothesis, yes, we can use probabilistic inferences to narrow down the choices, but it's not going to give us a unique one. It's not going to give us a unique set. At best, it's going to give us a fuzzy and small set of initial conditions.
All right, thanks so much. I think the next person I have is Shannon.
Hi, I was just wondering if you could say a little bit more about what you think the nature of theoretical virtue of traceability is, whether it's connected to other theoretical virtues that we may have commitments to, and whether or not, in some cases, it might be a defeasible theoretical virtue.
Yeah, thank you so much. It's a great question. So I think it's definitely defeasible. It's always this battle of super theoretical virtues, super empirical virtues that balance out after we've done our empirical investigations. And it is a theoretical virtue, I think, as connected to other theoretical virtues too, such as underdetermination, not by evidence, but by ontology itself. So you might want to say, well, I want to avoid underdetermination of theory by evidence, but we want to also avoid some kind of underdetermination of theory by ontology. It is not exactly a Humean idea, but it's somehow connected, I think. You want to minimize the gap between the ontology and nomology. You don't want the law to flow free from ontology. There's not complete determination, even non-Humean, but still you don't want this to be flow completely free in some sense. Even if there's no simplest, most informative guide, it is still, you want to have some kind of traceability criteria in the ontology. And that's, I think, the connection here. I think someone else suggested in earlier comments to my paper that you want to connect this to Occam's razors kind of reasoning, simplicity and parsimony. Maybe there is some connection there too, but I'm not quite sure yet.
Thank you.
Thanks so much. I think the next person I have is Diana.
Can you hear me now? Hey, Eddie,
yes.
thanks. I'm okay. How are you?
Good,
Great.
how are you?
Okay. Great job. I really enjoyed the talk. I'm sure a lot of it went right over my head, but I want to ask you something about the vagueness. Can you easily go back to the slide where you put up the different features of language that are usually regarded as constituting vagueness?
Yeah.
Thanks. It's not essential, but it just might be helpful.
Okay.
Those were right around where you put the Sorites paradox up.
This one?
Yeah, that's very good. Yes, thanks. Higher order vagueness. Okay. So, I mean, we'd have to talk for a long time about this, so let me abbreviate, and if it's completely incomprehensible, you can tell me. Those, at least 3 of those 4 features there that you mentioned, I would suspect they come apart. Okay, so I don't think, maybe some subset of those holds for vague language, but probably not all of them do. So for example, the Sorites paradox, it has to be solvable, I think, because if it's not solvable, then ordinary language is incoherent. And we know ordinary language is incoherent, right? So we just have to keep working on that paradox, I think. I think there are reasons to doubt the existence of higher order vagueness. We could argue about all that stuff. But suppose something like that, suppose those features turn out not to obtain of what we intuitively want to call vague words. What would be the effect of that on your view? So let me make one more point. I take it, well, what does if your view is correct, does it immediately rule out epistemicism about vagueness? Because on that view, the vague words really do have sharp boundaries. They are precise. It's just that we can't know where the boundaries are, right?
Yes, good, thank you. I think it's compatible with epistemicism, so that's why I added apparently here. But actually, when I do characterize nomic vagueness, I don't, define it in terms of this. I define it in terms of fuzzy boundaries or borderline cases, or in the words of Sanskrit, you can say there's boundaryless laws that can still classify. That's the kind of thing I'm going for. But this kind of thing, this characterization, I think are helpful in getting us there to the formal definition of nomic vagueness. If what I say is right, there's this dilemma between arbitrariness and vagueness, which is sort of the kind of arbitrariness where you have in natural language as well. That you might wonder, epistemicism is a just so story. It is incomplete story. It is somehow, defective and somehow. I think epistemicism might be more plausible in the case of nomic vagueness, but still I think we have to acknowledge the kind of trade-offs here we're playing. It's not complete free lunch. We have to pay somehow. We have to pay the cost of vagueness, or to pay the cost of arbitrariness. Either way, we have to pay something. It's not completely straightforward to say, oh, here's vagueness, go epistemicism. Yes, that's done. It's, I think, a very careful and delicate balancing act. In other cases, nomic vagueness, outside past hypothesis cases, you might have different kinds of trade-offs. That might be similar to this, similar to epistemicism, ordinary language, similar to other kinds of things. It's just something we have to be careful about. It's not completely straightforward, clear-cut.
Okay.
If ordinary vagueness disappears, that'll be great. Maybe that'll have implications for nomic vagueness too. If we can solve the Sorites paradox, then maybe we can solve the Sorites paradox here too. But also, I think there are constraints here that are not in ordinary English, right?
Can you say the last thing again, Eddie?
Sorry, there are constraints in nomic vagueness. There are not constraints in ordinary language. Say, right. in your theory of vagueness, if I understand correctly, there can be oscillations of borderline cases. They're still exact, but it will be, I think, hard to accept you have oscillations of, nomic possibilities, right? So that seems to be a case where it's disanalogous between ordinary vagueness and nomic vagueness.
I think that's right. Let me just say really quickly two things, and then we can talk about it some other time. First of all, I don't regard failure to accommodate epistemicism as in any, let me put it this way, I would regard that as a virtue of a view.
I see.
Okay, right? I mean, as a philosopher of science, you don't want to be supporting a view that says that vague words have unknowable sharp boundaries that are fixed by an unknowable function of their unknowable histories of use, right? I just can't imagine that. So don't worry about that at all, I would say. But one interesting thing I want to talk to you about more later on, I'll just flag this, is that I actually think that vagueness ends up being a form of arbitrariness. Mm. And so it's a multiplicity of reference, and the selection of which, the selection of any one of which is going to be arbitrary. So I'll be curious to hear more about how that might interact with what you're doing. But that's great. Thanks a lot.
Thank you, Diana.
Okay, I think we have time for one more question. We're a little over, but time for one more question before we move on to the general question and discussion period when people can continue to ask more questions. So we'll take one more question, then I'll turn off the recording and we'll go to our general discussion. The next person I have is Noel.
Hi, Noel.
Hi, Eddie. Thanks. That was awesome. So I was interested in, I mean, your talk was kind of largely pitched from a Humean perspective. And you mentioned at one point that anti-Humeans are going to be more resistant to this, but it strikes me that there are lots of anti-Humean views that are perfectly compatible with ontic vagueness. So like a Cartwright type view would be an obvious one. You could take a Lang-style view and replace stability under all counterfactuals with like most or many or something like that, and you get a similarly. So it seems like there are lots of ways for at least certain kinds of anti-Humean views to make sense of this. And I guess the question is just, suppose I were an anti-Humean and I went this route, are there other aspects of the arguments that you give that would sort of look very different from an anti-Humean perspective?
I was assuming, actually, I was doing this neutral presentation knowing vagueness, not assuming humanism. And I myself am an anti-Humean. And I think that Humean theoretical virtues are helpful guides, epistemic guides to the true laws. I'm, in that sense, a minimal anti-Humean, minimal primitivist. I think that the past hypothesis can be a fundamental yet anti-Humean law that can constrain the possibilities. There's nothing strange about that as the dynamical law. So I think the arguments I gave are more or less neutral between minimal primitivism about laws of nature. Minimalism, I think of it just as taking Tim Maulin's view, take away the restriction to fundamental dynamical laws, and you have some kind of minimal primitivism. That view and humanism, this should be neutral. If you accept the criterion that all fundamental facts have to be exact, then you have a problem with this view. But if you don't accept that, or if you think we should be empiricists about whether that principle is true, there's no problem, I think, no empirical problem. It's just that if you want to insist on mathematical accessibility of all the laws, then there is a problem. But that can be common to both humans and non-humans.
Thanks.
Thanks, Noel.
Great. I want to thank Eddy again for your talk. I want to thank Orly and Katie for your fantastic talks. I'm going to stop the recording now, and we'll move on to our general discussion period. So let me turn off.